in the solar type stars, the electrons in the atmosphere come from what we call the metals, all the heavy elements. We can't get electrons from hydrogen because there's not enough energy in the atmosphere to ionize hydrogen. You have to go to much hotter stars to ionize hydrogen in the atmosphere. So you get a solar atmosphere which has lots of free electrons, but they all come from the metals. And those electrons can pair with hydrogen atoms to form what's called an H minus ion. This is all very well known astrophysics. It's the first thing you learn when you do stellar astrophysics. Okay, and
Hmm.
I apologize it for because the biologists will never have done this, but you can generate these negative hydrogen ions in the atmosphere, and they're the dominant source of opacity in the visual spectrum of the sun. And that opacity has a minimum value where you actually disassociate the ion, and you can knock the electron off the ion with three quarters of an electron volt, 0.75 electron
Hmm.
volts.
Hmm.
And that produces a minimum cloudiness or mistiness in the solar atmosphere, which means that the light that comes to you from those wavelengths is coming from deeper in the atmosphere where it's hotter. So the sun doesn't emit a perfect Planck spectrum. It's hotter in the near infrared because of this minimum opacity in the near infrared.
Okay. So it
And
is the output of the sun.
the output of the sun is higher
Yeah.
by a fairly significant amount spread over wavelengths, as you can see. And this is the wavelength within which light can penetrate the body.
Yes.
And it seemed to me that the coincidence between the action potential that you need for all of life and this excess energy coming from the sun is likely to have driven the evolution of life
Yes.
for 4 billion years on the
Yeah.
planet
It sounds like
to bring
yeah.
these two into coincidence.
Yeah, it sounds like what you're saying is this is not a coincidence. Life probably adapted to this pattern of solar
Yes,
output, and that
yes.
is why near infrared light does all of the things that it does that we might start talking about next.
Exactly. Yes, it's not infrared light is not useless for life. It's a
Right.
fundamental part of allowing life to metabolize properly. In fact, we are willing to coin the term photometabolism to
Hmm.
describe this process.
Hmm. Hmm.
And it's the thing is, before biologists erupt in disgust, we say the photosynthesis is different. The photosynthesis
Right.
is using solar photons as a source of energy.
Right.
It's converting those solar photons into chemical energy. We're not doing that here. We're using the solar photons to catalyze a process of burning
Yes. Yes.
that food.
Yeah.
So
That's
it's a
so.
catalyst. It's a
Yes.
photocatalyst for metabolism.
Yeah, I'm glad you brought that up. So, yeah, I wanted to start to come to this. So, you're not saying that animals are doing photosynthesis like plants do, but you
No.
are saying that all life is using light from the sun, including near infrared light, which is
Yeah.
abundant, to catalyze or modulate how metabolism is happening.
Yeah.
And so
Exactly.
let's get into that now for animals. We're not talking about plant photosynthesis. We're talking about
Yeah.
mitochondrial metabolism. What do we know about this part of the light spectrum from the sun here, near infrared, infrared, and how it modulates what our mitochondria are doing?
Yes. Well, this is the problem we're trying to understand. Let me tell you what we think and what we know and what we don't know. We don't know everything yet.
Mm-hmm.
First of all, we have to get light into the body. If we're going to reach a significant number of mitochondria, it's okay for a fruit fly because the light can get in easily, but in a body, you have to get into the body. Now, how do you get light into the body? Most people would say light penetrates very small distances in the body, and indeed, in the visible, light does penetrate only to this layer of the skin, essentially. It
Can you
goes
do
a
stop
little
the
bit
screen
deep.
share?
Yeah, it goes. Yeah, I'll get rid of the screenshot. Okay, you've seen that diagram. Stop share.
Okay.
So the thinking is that in the visible, you only penetrate to very shallow depths
Hmm.
because you have such strong chromophores. You have strong pigments all through the visible. You have in bodies, in human bodies, you have hemoglobin. In plant leaves, you have chlorophyll. The visible spectrum is full of strong chromophores. As soon as you go into the near infrared, that situation changes radically, and that's physics. It's because, visible light has enough energy to move electrons around in atoms and molecules. So you can build chromophores which are very strong and very sensitive to being changed by an incoming photon. As soon as you move into the near infrared, you don't have enough energy in the photons to move electrons around in atoms and molecules very easily. I mean, there are a few, but those interactions tend to be very weak. You begin to run into water, which absorbs weakly as you go into the infrared. The water absorbs more strongly the further you go into the infrared. You're just seeing the high overtones of the vibrational bands of water in the visible and near infrared. So as soon as you move, let's say beyond 700 nanometers, you've run out of pigments. You don't have any pigments. You don't have any chromophores. Nothing's colored anymore. In fact, if you look at you're wearing a black shirt, aren't you? I bet you
It's
if you took an
yeah,
infrared photograph of that black shirt, it would be white
yeah, yeah.
because there aren't any pigments in the infrared. And so as soon as you start looking at light entering the body in the infrared, you're in a totally different scenario. In the visible, you're dominated by absorption. In the infrared, you're dominated by scattering.
Hmm.